Okay, thank you. So let's start again. So hello everyone, I'm Adam and I work for GrapeUp as a technical team leader. I am also a certified Kubernetes administrator and I took part in a lot of projects with GrapeUp associated or or where Kubernetes was being used. And a lot of them resulted in Kubernetes going to production. And so I tried to pick the things I have learned, I found out during those projects and this kind of situations, and share with you in this presentation, which is Kubernetes in production and lessons learned about resources management. So why resources management? This is due to a lot of situations which happened for me, especially on the production clusters where the resources were one of the biggest problem, but not the only one. So let's start. Okay, so what to do before your production takeoff? There are different origins of the idea of implementing Kubernetes in the company or in the project. Sometimes it's just a single person who decides, like CTO or technical leader, who says we need Kubernetes and everyone have to comply. Or it is a framework which is now deprecated, or just developers willing to change to something else, or just try to Kubernetes because Kubernetes is now on the top. And yeah, so it all starts with POC, with someone just trying it. In most cases, there are not a lot of people familiar with this kind of cloud platform because it's still quite new and it's changing a lot on even a daily basis. There are a lot of services created for it, and a lot of them are getting deprecated too. So there's always a lot to learn. I try to pick the things that matter the most in my experience, and I'm for sure not going to cover all possible cases and all possible situations, just the main examples I found out. And this will be based on Kubernetes, but the overall idea of the things you need to think about or take care about is common for most of the platforms. So if you don't use Kubernetes, that's fine. You can still try to think how you can use it in your project or on your platform. So what to do before the takeoff? I'm not sure if we have any pilots in the audience, especially now it's very limited list, so probably not. But what pilots do before their takeoff is the pre-flight checklist. And what the pre-flight checklist is the list of things that has to be done or checked before you even start your engines and start the actual flight. And I have gathered 6 things, maybe 6 categories, let's say, of things that were the most important ones. Some of them were the things that were often forgotten, or just things that I think were the most important, and lack of them resulted in huge problems. So the first category is limit. And what I mean by limit is to check if all required cluster requests and limits are configured for the pods and deployments and enforced. So it's not really helpful if you configure the request and limits on your pods and the new developers comes in and he just pushes something without the limits configuration and it blows up your cluster. So that's the first thing, first category. The second category is size. And the importance of size is visible, especially if you migrating a lot of pods or a lot of containers initially to your cluster. You need to calculate the size of the cluster so it fits all the deployments, but not just the happy path, the easiest case, but all possible solutions when it can grow up, it can scale up or scale down. And when thinking about the cluster size as a number, you need to also think of the auto-scaling part. So if there is going to be more workers coming in automatically or getting down automatically, which affects a lot the size of the cluster, but also the pods which are running on each of the workers. Or you would rather to have a static size of the cluster, which you can only put a fixed value and change only that value if you really need to, but nothing is going to happen automatically. The next category is access, which is about making sure that the users who are going to use the clusters, and by users, I'm not only thinking about the developers, but also the operators and administrators, that they have accounts which are useful for them in terms that they can do anything they really need to, but also they can't do something which is outside of their privileges. So that they can't add root accounts to pods if they are developers, or this is actually up to the company policies, but this is very important and we will come back to this category too. The next one is backup and restore. This is about configuring the backups and restores, and I have heard a lot about people who either didn't have backups, which is not actually that many. In most projects, they were backups, but in, I would say, 90% of them, nobody tested the restore. So there was a backup, but nobody cared about if the restore really works. And if it doesn't, and you have backup, your backup is technically useless. And the next category is monitoring and alerting. The monitoring part is important if you're looking at it. So if there is no alerting and you are not looking at it, there's no point. But if you have monitoring and alerting, if something wrong happens or something wrong is going to happen in the near future, then you are set. And the last category is the ownership. This sounds very similar to the access levels, but this is more about people than the configuration and the roles for the cluster maintenance. Okay, so this is the checklist, and let's go through the categories then in depth. So the most important thing I have learned is that you need to think of and plan your workload size and the cluster size and keep it under control. In a lot of projects, there were situations where there were no limits, no requests on the pods. And as a result, the cluster were crashing under its own weight. It doesn't really matter if the deployment, which has no limit set, is a developer pod like your application, web application, or Python backend application, or especially Java application, which can eat all the memory you have and more. Or if it's, for example, the daemon set deployed to the kube system, which is gathering all the logs and keeping a lot of them in memory, and it takes a lot of memory and this disk space and just affecting the performance of your cluster while it's hiding behind the kube system idea of things that you don't need to worry about because this is the shared service and it's not the developer responsibility. This is all very important. And to actually have a plan is one thing, because you can try to figure out how many resources you need based on the application, the count of the containers you're going to run, the number of deployments, number of the clusters, number of the workers. This is all just the numbers. This can be easily calculated. But the other thing is to enforce that. So you need to make sure that if someone runs the application, it has a correct configuration and it runs smoothly on production. So how can we actually enforce that? What we should keep in mind when we configure our cluster deployments, cluster containers, cluster pods? There are 4 things on this list, and let us go through all of them one by one. The first thing, which I found very important, especially but not limited to the autoscaling clusters, is pod disruption budgets. What does it mean that there is pod disruption budget? If you configure your application in Kubernetes, most people just run more than one instance of the application, 2, 3, 4, just a few of them, to make sure if one crashes, there is still something which can handle the load, and to make sure that if the pod is going to be moved or something happens with one container, there is always a backup. But this does not really prevent you or prevent the cluster or scheduler from moving both pods at once somewhere. Or, for example, the easiest example that happens, it rarely happens when you start deploying your production clusters. In most cases, it happens in a week or in a month. You need to upgrade your workers. And to upgrade your workers, each of them can have to be killed and recreated. And all pods running on the worker is, of course, evicted. So Kubernetes will kill the pod and move it to the other worker. If there is no pod disruption budget configured, this means for the scheduler for Kubernetes that it can kill all the pods. If there is pod disruption budget configured, it means there is a number of pods which have to run simultaneously. So if we have a deployment which has 2 replicas configured and pod disruption budget set to 1, it means there has to be at least one pod running at a time. So if Kubernetes is going to move your application, which consists of 2 containers running on a single worker, to the other worker, it will kill one of them, start it on the second worker, wait for it to run, and then it will kill the first one. This is very important for the container upgrades, for the stability of your solution. And this is the first thing you need to think of. The second thing you need to think of is limits and ranges. And this is a strange thing because if you start with Kubernetes, you run your first container, or you start from the Docker, it's often forgotten because if you run your application and you don't configure limits and ranges, it just runs. And in a lot of cases, it doesn't even require them. If you run your containers as a Lambdas or on a Fargate or ECS on AWS, you might not even think about the limits and ranges a lot. But if you don't configure limits, it means the container can take as many resources as it wants. And if you don't configure requests, it means it initially will take the minimum it requires to start. So, for example, if you run 2 containers and each of them starts with 100 megabytes of memory usage, and then one of them grows to 10 gigabytes, of course, the other one doesn't have any space, and you can run more of them on this worker. And there is a specific setup for both CPU usage, CPU millicores, which is 100th of the core, and the actual amount of memory being used. The third one is the priorities. So even if you configure limits and ranges and disruption budgets, it's not like all workloads, all containers, all deployments you run in Kubernetes have the same priority. Some of them are mission critical, some of them are supporting or supplemental. You don't need to worry about these supporting ones, like gathering logs if your application is down or this kind of things. You need to make sure that mission critical ones are not interrupted. And to make sure this happens, you need to set a higher priority for them. The priority is very important because it overrides even the pod disruption budget. If the scheduler sees that the situation, the quite complex one, where you have an application which has to be run, and you have the second application with a higher priority that has to be run too, and there is only space for one, it can even violate the pod disruption budgets to make sure that the higher priority one is going to be started. So this is the configuration value which you really need if you have a mission critical services in the cluster and the ones that you don't really care about. that much. And the last thing, which is actually associated with the limits and requests and ranges, is the quality of service. And the quality of service is not actually the configuration value. It's not something you can set on a pod by just typing in, I want QoS guaranteed or burstable. This is a configuration which is, it is actually a status which is assigned to the pod when it has a limit and a request configured to the same value, or just limit with no request. What it means for your containers, for your cluster, is that if you have the same limit and request set, the quality of service status will be guaranteed, and it means it only can run on a worker which has a space for it, and it should not be moved from that worker if possible. So if you set the requests and limits on all your containers on a worker, effectively you're setting a fixed size of your deployments. You are making sure that the Kubernetes is not going to move your pods, to move your containers to affect the layout on the worker. This doesn't sound like something you really might need to do in most cases, because the huge advantage of the Kubernetes is that it can move the pods, it can move the containers, it can schedule them flexibly with flexibility, which allows them to run in cloud. But sometimes the more important thing is to make sure that the clusters the cluster and the containers on it is not interrupted by the scheduler moving containers between the workers. So if you configure all four things, you're affecting the scheduler way it thinks of your applications, and you're making sure that the most important ones are running smoothly. And at the end, I will show a small example how it actually affected one of my projects. But let's go to the next slide. So the next thing, which is part of the backup and restore, is and actually also a part of the cluster resources and cluster size maintenance, is that you need to keep an eye on the storage in the cluster, and you need to think about that there are three types of storage in the Kubernetes cluster. And the one which comes to mind initially is always the persistent volumes. So the volumes which are attached to the pods, to the containers running in the cluster, for the containers which require non-ephemeral data, like database or this kind of things. But this is not the only one, and there are two more which are actually affecting each other. To the pod, you can attach ephemeral volume, or like empty dir type of volume, which is using the local storage of the worker. And this means that is effectively affecting the available size on this worker for disk space. And this disk space is not only used by the containers, but also by the node local or virtual machine local data. Like Kubernetes workers obviously have logs, but also it has a Docker running or LXD running or any kind of racket or solution which runs your containers. And to run your containers, it caches the images, and those images need space. So if, for example, logs of the application, which are put on the ephemeral storage, are taking a lot of space, 90% of the node, and then you try to pull a very big container image, it may fail. So even having an empty dir, which is considered as ephemeral storage, can affect the cluster performance greatly if there is not enough disk space. So backing up, the thing with Kubernetes is that it's based on always installed on a cloud. And there are different types of clouds. There is AWS cloud, there's Azure, but there can be a local cloud or Barebone. There is something which is running the workloads. And Kubernetes tries to abstract the cloud, the infrastructure which it's running on from the actual aspects of the kube system and APIs. And the problem with that is the storage and networking. There are a few things which are dependent on the cloud. And those are configured as a plugins. So there is network plugin, there is a CSI, a storage plugin. There are plugins which inject these cloud things, cloud provider specific resources which are required, for example, also load balancers, to the cluster. And this also means that there is no, as of me speaking right now, because it might change in the future, but for now, there is no common way to back up the persistent volumes. There is a tool called Valero, which handles a lot of cloud providers for the backups, but Kubernetes on its own doesn't allow backing up the volumes. So you need to consider this yourself. It doesn't matter if it's Valero or if it's a cloud provider solution, like AWS can take a snapshot on the volume, that's also fine. But this is something you need to consider on your checklist before going for production. And if you don't want to back up the cluster itself, you can use, obviously, Terraform or Ansible to create it from scratch. And for me personally, the Terraform or the Ansible, it's the best way to create the Kubernetes clusters. Doesn't matter which cloud it's running on. But this is not the perfect solution for restoring it. You can restore the workloads using CI/CD pipeline, of course. But if you want to restore the volume snapshots that were there, you might need to restore the whole etcd, which is the database holding all the cluster informations on its own. So Valero also allows to back up the etcd, and there are a lot of solutions which allows to back up the Kubernetes database. And restoring it in most cases is safe. So if you can, it's very often better to back up the etcd too. If you can't, then you will probably have a problem with restoring the persistent volumes and attaching it to the correct pods and deployments. So least privilege access. There is, of course, in Kubernetes, a role-based access control, which is a configuration which says which user or which account can change or access any of the cluster resources. But this is often not enough. Sometimes you need to enforce the rules or policies, which are not strictly resources, but the way the resources are handled. And with that, the Open Policy Agent, or OPA, can help. OPA works as a webhook to the Kube API. It injects its own webhook and sets the policy engine, which checks the list of policies you have deployed and configured in the Kubernetes, and checks the manifests that are being sent to the Kubernetes, and thinks if it should be allowed or denied. And you can put any kind of configuration or rules to the policies. So for example, you can even say, I want to run only containers or images from a single repository, or I don't want people to have the specific configuration, like a root user, or even configure users for the containers at all in pods, or disable a huge part of the load balancers, but only allow a single type. This is all possible with OPA. The one more thing, which is the Kube API access based is actually accessing the cluster. I have seen a lot of people trying to figure out how to access the cluster, and there is built-in Active Directory, LDAP configuration, and OpenAuth which can be used. And really, please use that one, because if you use the certificates and private keys to access the cluster, this is a nightmare, especially in terms of sending these keys to new users and trying to figure out who can access what with this key. If this is single sign-on, you can obviously use role-based access control to make sure that people don't have access to something they shouldn't, but still they can log in easily to the cluster. And the last thing about privileges is, of course, firewalls. Firewalls are, in most cases, external to the cluster. But if you want to enforce network policies inside the cluster, you need to consider using a specific CNI like Calico. CNI is the Container Network Interface. And the default one, which is Flannel for the Kubernetes, doesn't have an ability to enforce network policies, which are internal firewall rules in the cluster. So if you if you are in a position where you need really to have a network policies on firewall inside the cluster between namespaces or even inside the namespace, you need to consider a very specific CNIs. Okay, so next part is the cluster ownership. And I have divided it into 3 parts. And there is no one best solution in here. Someone always have to take care about the infrastructure. The cluster is running on something, on the VMs, on the networks, on the load balancers. There is there are always resources which are backing it up, and someone has to take care of them. And if it's not your team, you need to make sure you have a way to escalate any problems, and you have a way to debug the problems. Because if there is no communication between the workers on its own can work correctly, but still you need to figure out why the pods cannot access each other, for example. So that's the one thing. The other thing, which is obvious, is the cluster ownership. And from the DevOps perspective or the operator perspective, this is the ownership which is the most important and the most obvious for you. This is your cluster, you need to take care of it. But sometimes if this is like a team which has mixed competencies and like DevOps roles inside the team, sometimes they want the cluster on their own. And still, there has to be a monitoring if they are using it correctly, and they cannot just do whatever they want. There has to be a specific set of roles and requirements for them, how to run their clusters. And still, you need to make sure that you know what they do. And the other way around, because if someone is running their workloads on your cluster, you cannot debug them in most cases, because you don't know what's inside, what code was deployed, who's working on it. In this case, there has to be an access for the development team to at least logs, but also sometimes to SSH to the container to see what's running in it. If you have a connection to the internet or whatever is required. The access to the cluster for the developers cannot be limited, but on the other way around, the operators of the clusters often shouldn't manage the workloads running in it directly, but more like setting the policies with OPA to make sure that they are not doing something very bad to the cluster, but still have a lot of freedom on running their workloads, their containers. The next part is monitoring and alerting. And there are 4 basic things. Monitoring infrastructure, so making sure there is always a disk space on a master and a worker. The CPU usage, memory, and network is fine, especially network, because if you have a problem with DNS in the cluster, which happens quite often, then you will see a very huge spike on the network usage, which will show you the problem even before the memory usage of the DNS pods will rise drastically. The other thing to monitor is actually the Kubernetes services, which is one of them is DNS, but there are a few of them running in the kube system. And it really depends on your installation, but sometimes it's forgotten that those are also containers. Those also should have limits and requests and ranges configured, and those also should be monitored, because if your DNS is running at 99% of the memory usage or CPU, it might crash, and without DNS, the cluster is going down. And of course, even if you don't manage the workloads, the containers in other namespaces running on your cluster directly, you still might want to, you should monitor them and see if they are crashing. Maybe they are in a crash loop. Maybe there is not enough space for some of them on the worker, and escalate this kind of issues to the development team. Or even check if there is not a problem with scheduler trying to pull image which doesn't work, which is also visible via monitoring. But even if you have all of this configured, for example, let's say with Grafana or New Relic, there is one thing which is important, which is alerting. And if you have monitoring without alerting, and you don't look at it, there is literally no point. If you don't look at monitoring and you don't have alerting, you don't know when something breaks until someone comes to you or calls you in the middle of the night. So the alerting configuration should be done in a way, it's not saying something is broken now, but it should say something might break in a day or in 3 days or in 7 days. The default configuration for Grafana Alert Manager, or Prometheus Alert Manager, sorry, is that it has levels of notification. So it doesn't alert you only when something breaks, but also if the CPU usage is high or memory usage is high. Alerting is important when the accident happens, but it's even more important before it happens, so you can mitigate the issue. And if everything goes wrong, because you don't configure limits or you forgot about the pod disruption budget, what can happen? What happened to me personally is a big crash of the storage system. And the result was quite spectacular. There were dozens of evicted pods. A lot of them were out of memory killed. The deployments, even the system ones, were pending, so it was not even possible to figure out why it's not running, and some of the cluster daemons went down. The most obvious one was the evicted pods, but all of them resulted in a huge crash. So let's see the timeline. There is a rookcef solution, which is a storage in a cluster. It's using whatever you configure, in either ephemeral storage or persistent volumes, to store the data either as different kind of persistent volumes or as buckets. And the idea was to have a terabyte round of the storage in the cluster, split into, I think it was 6 or 10 containers, which were running on a single worker, a big one. And there were, I think, around 100 workloads, saving a small amounts of data, but constantly to this storage. And it was getting cleaned up every, I think, around a few hours, 2 or 3. So it was never full. It shouldn't be ever full. But the data was important, and it was copied over to the other place. So at the evening, the rookcef was installed using the official Helm chart. The documentation is very bad, so unfortunately, the the examples were used to install this Helm chart, and to actually figure out later on how to configure it properly, it is required to just read the source code on the GitHub, because the documentation doesn't really help. So the configuration were done based on the example, so that there were 9 storage pods on 3 workers, as I wrote here. So there were 3 workers instead of 1. And I think it was around 120 gigabytes each pod, which resulted in around 1 terabyte. There was a monitor running, which manages all the storage pods. There was a manager running, the UI dashboard, everything worked fine. And the deployments, which were saving data to the Ceph cluster, started around 10 p.m. And it should output around 250 gigabytes of data. And obviously it was 10 p.m. We managed to start it and we went to sleep. Nobody were monitoring it because it should be a solution, a bulletproof one. So we went to sleep, and next day around 4 p.m., so after quite a lot of hours, 16, I got a call that the Ceph storage is not accessible. The size shrinked from 1 terabyte to, I think, 200 gigabytes or 300. The data cannot be saved, the data cannot be retrieved, and nothing is really working on that deployment. Not just itself, but the whole cluster was not really functional. And what we did is to restart all the pods, and it started to run. But this time, we actually monitored what's going on. And we have noticed that the Ceph has undocumented feature of storing the data in memory as long as there is a free memory in the container or in the VM which is running on. And as a result, one of the containers had, I think it's 32 gigabytes of memory used. All other ones got evicted. So 600 of gigabyte of storage was lost. And the Ceph tried to run them, but the pods were evicted and didn't run actually. And what Kubernetes does in this situation, it tries to run the next ones. So when we came back, instead of 9 pods on the list, there were around 50 of them, each trying to run and crashing each other, and everything went down. And after that, we found configuration, which is not in the documentation, but only in the GitHub, in the code for the Helm, that there should be a limit set. And we have configured limits, requests, pod disruption budgets, and technically fixed the size of the Ceph on this worker. So it filled all 3 workers with the containers without any space for anything else to run there, to make sure it doesn't get evicted. And the limit was enough to make sure that it's not going to crash. And it ran for, I don't know, weeks without problems. So this is what might happen if you don't configure limits and PDBs. But I hope after this presentation, it's not going to happen to you. So thank you.